Okay. Is this one?
Yeah.
This one.
This one.
I feel like Taylor Swift with this thing on. Okay, good morning, everybody. Yes, my name's Raphael Shirley. I work at Max Planck Institute for Extraterrestrial Physics with Mara there. Also, this work is done with Olivier Hilbert and Johan Cohen-Tanugi, based in France. I'm mainly working on LaFar, the template fitting code, but I'm hopefully going to give an overview of the state of photometric redshifts for AGN in general. And yeah, my work is concentrated on preparing for Vera Rubin, the observatory. So I'm working on the German in-kind contribution. So I began just over a year ago in 2023. So LaFar development has concentrated on galaxies in the past. Mara has, of course, done lots of work on applying it to AGN. But we've been extending the AGN part of that, and that's, like I said, a big focus of my work, building on her experience in these deep fields with the very good multi-wave coverage. On LSST only data, but you know that the importance of that multi-wave is eROSITA is a key focus of our work in MP, and I think Mara's going to speak in great detail about the eROSITA data release. But you know, we're developing a general code for all uses, and that's our science focus. But yeah, the code should be general, and we're not, as part of the in-kind, we're not performing large-scale production runs. But we're working on the code such that it can be run on a large scale. And I think in reality we will be performing runs of the codes, but you know that's not something we're obligated to do. I think that's something that we need to think about quite seriously actually going forward. But this is an overview of me. So that's just to introduce myself, but to talk in more general terms. A big question for us is template fitting or machine learning. And I think if I want to emphasize the importance of using both together, so using templates and machine learning together, starting to think about how we're going to do that, which method is best for which purposes, and how can we combine them. So to go over the differences, machine learning, one of the real pluses of it, we see very high performance on samples inside the training space. So I think it can really outperform template fitting on a given sample. It's easy to use additional input, by which I mean template fitting is essentially we have a measurement of flux in every band. But the real advantage of machine learning is we can start to look at pixels, we can start to look at morphology, conceivably variability. We can essentially sort of throw every informative piece of data we have at it. We can use all that information, which is the real advantage. It's very fast to run after training. So we've got these huge catalogs coming from LSST. That's another key advantage. Training, of course, is slow, but what really matters for these large data sets is the cost per object, and that really is very low for machine learning. Poor handling of rare objects, I think it's a real drawback of machine learning. So objects that aren't really captured in your training space, or conceivably when you just have a small number of objects without any training space at all, then machine learning effectively cannot be used. And it requires retraining new data. So if the noise improves, or we have a new area of the sky that needs to be retrained. Template fitting, on the other hand, is physically motivated. So we have these physical models of the SED, which is a real advantage. It means we can look at the templates. So when we have a fit, we have a best template. We have considerably physical properties for that template, for galaxies, stellar mass, or other properties such as that. No training set required, obviously a key advantage. That in turn means no training set bias. One of the things that the dark energy science collaboration really cares about, for instance, number counts. Often what we've seen with machine learning that you train on a spectroscopic sample, you essentially just reproduce the number counts then in your final measurement sample. And of course, we can probe new regimes. The best example of that is these high redshift objects in JWST. that's a real power. We're hoping to probe new regimes with LSST, so that's very important. Statistically robust. I think we understand the statistics. It's based on very well understood uh, square minimization, and we understand how that works. Whereas machine learning, of course, can be a bit of a black box. I think that's less true than it used to be. Someone was asking me about the posteriors on machine learning. I think that is generally the case now that machine learning codes are producing full posteriors. So we do have good measurements of the errors, which used to be the case. But I think it is fair to say that the statistics of template fitting are more robust and better understood. And of course, it's the only method for small samples. But the key conclusion of what I want to say is we can use both together and start to think about how to do that. So I've shown this slide many times before, but just to highlight the challenges with SED fitting for AGNs. The examples model here, I think it's a really clear way of showing the basic AGN SED. We have this negative power law continuum, which is of course degenerate in normalization of redshifts. So if we concentrate on the left side of this diagram, it's flux density against wavelength. So we think about the LSST bands, that's the sort of 6 leftmost bands, and we're not capturing this rise that we start to see with the dusty torus. We've just got this negative power law continuum. So really, only when the Lyman break moves into those filters do we start to get very accurate redshifts, or more accurate redshifts, sorry, above redshift 2. But there really aren't many features there. We have, of course, the broad bands, but there are real limitations on what we can achieve with SED. So I think this is a really key figure. Obviously, the key method that all photometric redshifts are using is color redshift relations. This is one particular example from Mara's 2022 paper on the EFEDS, the eROSITA Final Equatorial Depth Survey. And on the top here, we're seeing point sources, and the bottom row, we're seeing extended sources. And then I'm looking at IZ color redshift space on the left, and then double WISE W1, W2 redshift space on the right. Of course, we don't have the WISE colors. We've got every object in SST. And it's sort of showing you problems of degeneracy in one color. But the basic method, of course, the black points are spectroscopic objects. So just sort of to think about what a machine learning code is doing, we measure a color. So let's say we measure IZ equals 0. And then what a machine learning code is doing ultimately is looking across that redshift space and have a distribution of the spectroscopic sample in that redshift space. Whereas, of course, for template fitting, so the lines here are templates, we're looking at the measured color, we're looking at all those templates, and for each template we have a best fit redshift. Then we marginalize over those templates, and we get a redshift distribution. Just think about this example here, what machine learning is going to do. Okay, we've got all these spectroscopic objects here, and we're going to give you a distribution of along here. But these templates here, these may well be correct colors for these templates that aren't covered by spectroscopic sample. So machine learning is going to give us this distribution of these spectroscopic objects, but we're not going to capture this space here, which may well be true. And that's sort of the real importance of template fitting. It's a simple color redshift diagram. We're all familiar with these, but I think it's important to think about the difference between the two methods and how exactly they're working. I think it's sort of a philosophical difference. I've been reading some of the philosophy of science literature on machine learning recently. I think it's sometimes described as a theoretical machine learning. Of course, with templates, it's much more theoretically driven. And I think that's sort of a good example looking at this space here at a given color and how that isn't necessarily captured by the spectroscopic sample. So I want to quickly say something about some work. This is from William Roster, a PhD student at MPE, and this is what we can do with learning. I mentioned that we can extend the method to other input spaces, and of course, pixels can be very important. So this is showing how he has a convolutional neural network which takes in a set of images and in fact color images, pixel-based colors. And I think that fundamentally what this method is doing is it's learning that there's more information in the host galaxy. It's learning to sort of look at the features in the galaxy as opposed to the AGN in the core. And it's learning that constraining sample. And I think this basic idea, the host galaxy that we can investigate with the extended objects and the outer part of the image. It's also been tested very thoroughly in a recent paper from MD by Aman Saxena 2024, which is showing a similar method but with aperture photometry. So William Roster's code is using the full pixel data, but we have recently shown the importance of this aperture photometry. And of course, in LSST, we are going to get these aperture photometry measurements. But I think particularly for extended objects, where we know we can get better performance with template fitting too, because we're host dominated. That's somewhere where machine learning is really powerful. And I also want to mention some other, again, Mara's work on eFEDs on the left there, and then again William Roster's work here on the pixel code using images, showing how we can get very good performance when we do have these additional data sets. So either in eFEDs where Mara has um, photometry legacy survey where we've got optical near infrared and mid infrared, we can get quite good accuracy there. So we're seeing an outlier fraction of 14.1. I really want to emphasize that that's a subset of objects. We are hoping to have these data sets with force photometry in near infrared and WISE. I previously worked on the UK in kind contribution, which is doing joint photometry with Vista. I think that's really important work, and it will give us good redshifts on those objects that have detections in near infrared and WISE. But yeah, I really want to emphasize that that's not true for the majority of objects. The brokers are going to want to have redshifts for every object we have on the sky, and lots of those objects we're not going to have near infrared and WISE for. I think it's important to realize the kind of accuracy we're going to see on those objects too. So the basic procedure, this is going all the way back to Mara's work in 2011, is essentially to split the sample AGN into quasars and extended objects, more host-dominated AGN. And this particular example, we have X-ray fluxes. This was a Chandra sample, and we can use the X-ray flux to further split it. And then essentially there were three sets of templates, two sets of templates actually, but three basic settings for the running of the FAR. This also involved a correction for variability. This is something that I think we're quite concerned about, is when we're using the deepest coads and lots of the AGN have variable photometry, how is that going to affect those general photometry measurements? So one of the ideas that Mara has is to use single epoch photometry to measure redshifts on a single epoch, where we know conceivably the colors are more consistent in a single time space. But obviously, again, to emphasize that the deepest data, the deep coads, won't necessarily have good detections in single epochs, and that is a limitation that we're looking at average flux. These deep catalogs are going to be averaged over time, and that's a limitation. But for this particular work, yeah, we had AGN-dominated library with an absolute magnitude prior here. These are essentially fainter objects, sources and variable objects, and then for the host-dominated, we use if they have a low X-ray flux, they get a standard galaxy template, and if not, we use an AGN-dominated template library. One of the advantages of the current incarnation of LaFar is that galaxies and AGN are fit simultaneously for every object. So for every object, we have a best stellar template, we have a best galaxy template and redshift, and a best AGN template redshift. But the absolute magnitude prior is set per object, so that requires a little bit of thought. And obviously, in this simple case, we're just having a separate absolute magnitude prior for extended or unsourced or variable objects. But I think we probably want to move to something like an absolute magnitude prior, which is dependent on the variability, to give us some sense of the importance of absolute magnitude for further constraining the redshifts. So LaFar, the code itself is originally a Fortran code. As I mentioned, it's a spectral energy distribution fitting using a set of templates, spectroscopic measurements, or modified models. There's a new C++ version. Actually, this is the official version, which you should be using for science, but one of the things I'm going to be presenting, a new version, actually, which we've made a lot of improvements to. It has a Python interface. I think for a lot of us now, we grew up on Python, so I think a lot of the code can be run straight through Python, which is very useful. As I said, stars, galaxies, age going to fit separately. And the core of the algorithm is a chi-squared fitting for every template, selecting the model with a minimum chi-squared overall and maximizing over the templates. One of the key things I've been doing over the last few months is working on the Link Incubator project. So this is the LSST Interdisciplinary Network $22,000 grant for us to work with 2 software developers. This was mainly Drew Oldag at University of Washington, also Olivia Lin, Jeremy Kubica, also working with Johan Cohen on the European side. And this was from February to May 2024. And we've basically conducted a C++ Python rebase. So we haven't changed the algorithms, but we have completely, we've updated the code. And a key part of that is the continuous development, making it much more robust. And so one of the real main outputs, I think, is pip installer var. So really, really happy with that. I think it makes it much easier to install. We can make you guys more likely to use it. It's easier to install. And the Rail interface is something I'm going to talk about in detail. So Rail is the Redshift assessment and infrastructure layers. This is the DESK, Dark Energy Collaboration project. They want to have Photo for every object. They've mainly been concentrating on machine learning so far. But I think by putting the VAR into Rail, this is a really important part of our inclined work. It means that those large desk runs are going to produce Redshift on every object in the LSST catalog. It means we can have AGN Redshifts for all of those objects. Now, a bit of a political point here. I think Desk has no obligation to share that data with the wider LSST community, and I think they will do that. But on what timescale, I don't know. So that's a really great thing. We're going to have these AGN Redshifts on every object. But I think we also need to be thinking about our own runs when we're going to get these. We might want to do different runs with different priors and things like that. I think this is a real open question. It's something we need to think about. I mentioned that we're not due to perform large-scale runs, but we're all aware of the importance of photometric redshifts. I think a lot of us are going to want to have template fitting redshifts. I mentioned the brokers. I think a lot of those, we want the brokers to have access to PhotoZ for AGN, where we've got variability. Okay, thanks. And that's something we need to start thinking about. So Rail, the redshift assessment infrastructure layers, it allows us to produce these posteriors for far, in addition to the other machine learning codes. We then look at point estimates. It has a lot of plotting functionality for checking metrics on the point estimates. We're using these pit plots a lot. This is probability integral transform. It's where we look at the integral of the posterior up to the truth, and then the distribution of those CDFs. And if we're drawing from the posterior, this should be flat. I think the way to think of these curves is if it's flat, we're doing very well. If it's peaked in the middle, that means it's over dispersed. I think it means that your spectroscopic sample is overly in the center of your distribution, and if it's like this shape, it's under dispersed. That means to kind of calibrate your posteriors, check that you're getting good errors. The FAR doesn't take account of the fact that templates aren't fully covering the true space of models, and therefore, if we have a template set that's too small, these can be under dispersed, and we can calibrate that using like smoothing with a Gaussian smoothing kernel. We can also add some background so that we're taking account of the outliers, and we can also modify the errors to take account of systematic errors to make sure that these probability plots are flat, we don't have large outlier rates. And this is something that we're running through Rail now, and it's very useful. And I think it also means that the next people are doing work for us in checking our results against their machine learning codes, and also hopefully providing a service to them as well. I mentioned this useful feature of the FAR is that it produces galaxy and redshifts for every object. So after the fact, if you decide it's one or the other, you can get both values. So one thing I'm looking at the moment is the clouds data set. This is the Canada, France, Hawaii telescope, HD Large Area Survey. What that's giving us when combined with types of PrimeCam Grizzly is, I think, a kind of LSST-like data set. And this is where I'm really starting to look at what the performance is like on LSST-like data. I've crossed BPZ out there because I haven't updated the filters. I'm just to point out, I'm running through BPZ. It's another template fitting code, and comparing to that. Don't look too carefully at the actual values because it's not a fair comparison. Those templates are are not correct yet. But I mentioned we're getting better performance with machine learning. So this is a KNN and FZ-Boost, two popular machine learning methods. That's understood, that's not a surprise. But I think I see them as useful benchmarks. This is important work checking the performance on LSST-like data. These are the galaxies showing you AGN, and again, this it's not pretty. We're seeing 20% outlier fractions, relatively low accuracy. I think we need to face up to the fact this is what we're going to see on LSST only data for AGN, and we need to start thinking about how we deal with these large outlier fractions, how we look at things like secondary peaks in the posterior to understand that most of these outliers hopefully are captured in secondary peaks, and learning to work with this quality of data for full LSST samples. Here's some point on the nature of the training set and how obviously for the full clouds data we're peaking at 26 magnitude here. Training sample, the spectroscopic sample, and this is Cosmos, remember, where we have very deep spectroscopic samples, where we're peaking at more like 20 below 23. That obviously means all these large numbers of objects here, fainter objects, are not captured well in that training space. And I want to show you sort of the impact of that. So what I've done is I've degraded that spectroscopic sample even further, cutting the spectroscopic sample in I-band magnitude, and then we expect to see this. We cut that training sample at say 1.5. We're obviously losing all of the high redshifts objects, and the performance of the machine learning code KNN is obviously being degraded. And this slide is really to advertise the utility of the template fitting, that we don't see this at all with template fitting. We're not getting this terrible degradation when we have unrepresentative training samples. Now, of course, you can build your science samples to be captured by the spectroscopic samples, but do you want to limit your science samples to magnitudes? Probably not. So I think this is just showing the importance of using template fitting. I've been doing a lot of work on priors. N of Z priors are very important. I've implemented a general prior. This is an important part of the work. I think I'm going to have to skip through this quite quickly, I'm afraid. But yeah, I've been talking a lot about the philosophy of priors, and we need to take care with the use of priors. But this has been implemented in a far. You can implement any prior you want. I think that will be useful for lots of people. We also have the capacity for classification. I'm really going to skip ahead there. We have rock curves available for this use of LaFar ratio between AGN and galaxies. It's another important use we have for every object. We have these best fits. You can use it for classification. It's of limited power, but we will have this available with every object. And yet, thinking about future work, optimizing parameters for LSST, possibly building an emulator, thinking about the max runtime we have for objects, and some other things. So yeah, just to conclude, this is a 3-year in-kind contribution, as I mentioned, doing a lot of work on the priors now, redshift priors, possibly from machine learning. The Link frameworks incubator is very important. The FAR is incubated Rail, the disk software, and we're working on optimizing the hyperparameters for template fitting currently.
Thanks, Raphael. There are 3-4 minutes for questions. First, possibly young people. Young. It's nice to see how young you see yourself. Yeah. So, normally people ask you how you identify yourself. Then yes, you are younger than me.
Yes. Thank you, Raphael. It's all really interesting work, and it's good to see it moving forwards, especially with the Link incubator and the pip install button. The questions you mentioned about the desk, doing large-scale desk runs, did I hear you correctly when you said that the desk is only running on the deep coads and not on the individual epoch images?
That's my understanding, yeah.
Okay. Yeah. And so have you done any back-of-the-envelope calculations? How much computing time would we need to do LaFar on every single epoch sort of set of colours for the AGN candidates?
So I think the answer is kind of it depends, because obviously, like, we can tune the hyperparameters for speed. We can use sparser redshift grids, things like that. So I think I'm not going to give you a CPU time per object, but it is something to look at now, and it's something with this short data set. I'm working on the hyperparameter optimization. I think we want a kind of reduced run on a sparser redshift grid that could be run every epoch. That's what we need to be thinking about, I think.
About your outliers, I was wondering if those are failures or are interesting objects. So can we dig something out?
We can be optimistic and say, yeah, they're interesting objects. I mean, they're objects that are not captured by the templates, I think, is the way to put that. That's definitely interesting. Yeah, but I mean, one of the points we're seeing is we're seeing similar behavior for the machine learning codes as well. What I haven't looked at is, what the overlap is between those outliers. We've seen similar objects being outliers for machine learning and fitting as well. That's something I haven't looked at. But yeah, possibly interesting, absolutely.
My question is, so for the classification, is before you apply for the 2D or is all together?
For classification, so we have a best model chi-squared for the best galaxy model and a best chi-squared for the quasar model, and then using that ratio of chi-squared as a classifier. And I showed like with just UGRIZY, that rock curve that we showed quickly at the end. This the best classifier in the top left corner, for a given level of purity and false positive rate. It's not a perfect classifier, but I think you could definitely generate samples from it, and it's definitely useful, I think. And that's something that we only get with the template fitting. So machine learning code, you have to train a separate classifier. We just have that by default. I do think that's an important and useful thing that will come out running on every object. Yeah.
Yeah, should be true. You show the color as a function of redshift. I mean, thinking about very extreme variable, the sort of the changing look type. I mean, is that range of the template covers by the color space is significantly larger than the expectation what we would have for color variation of the changing region, or that color of the changing region itself is much larger than the coverage of this colors versus redshift that you show. I mean, do you have any feelings or?
Um, so you're talking about a changing look AGN where the template is changing and the color space. We might want to talk about that later, I think. I haven't thought about that in detail, yeah.
Degeneracy when you have less colors to use for the degeneracy. So it's really you have multiple, but it's better to correct for variability to ignore it. So the next is, so I was saying, we are going to have the priors in left part. One of the priors is indeed the variability. This is the work that Sarath is doing with Roberto trying to get for this variability.
Hello. Okay. I almost feel like I'm wearing a helmet. Yeah. So the people who doesn't know me, I'm Sarath Satheesh, and I'm a PhD candidate at the Instituto de Astrofísica Andrés Bello University in Santiago, in Chile. And I'm working on training photometric redshifts using variability as a prior. It's just one of the priors that is going to be that is going in along with the other priors that people are using. And I'm working with Roberto and Timo and also Paula variability and stuff. So first of all, thank people who are here. I see that the number has been exponentially decreasing since the last week. Yeah, 62. Okay, that's right. Yeah. So as we know that what I'm trying to do is to link the redshift equations with variability. So here we have the quasar, and we all know that the quasars are varying and their intrinsic variability. There are many reasons that has been or many populations that are being brought to understand why there is particular reasons of variability, and if you include the instabilities in the accretion disk, where the accretion disk are considered as different, concentric circles with different temperature profiles, and maybe the difference in the accretion rate, or it might be obscured. So there are different possibilities that are being brought to study why the quasars really vary. And people are pretty much aware of different populations. Okay, so the most important model or the most famous model that the people study quasar variability is through this DAMP work, where they can easily understand the time scales of variability, the damping time scale, and magnitude of the variability. So here, or the one of the ways to study this variability is through structure function, okay, statistical measures. And here you can, on the right, you can see a typical structure function of a typical quasar that is being plotted with the along the amplitude of the variability and sorry, the amplitude of variability and the difference in the measurements. Okay. So the motivation for doing this study. So the primary motivation is that if we have to learn this or study these quasars in really large samples, particularly considering the variability science, so that we can really reduce the random variations, and also we can separate the intrinsic agent variability with other extrinsic variability that we see maybe due to microlensing or other features. And also we can understand the time scales of variability in a more statistical way. And also when we study these quasars in really, really large numbers, we can really understand the relationship between the agent variability and the redshift, and thereby the cosmic evolution. So that's where is going to come in. It's going to be a wide, fast, deep survey with its exceptional cadence and also with its competent coverage with Euclid and the so we are going to have a really large samples of AGM, particularly and but the selection and particularly the estimation of photometric redshift from we have photometric data is it's pretty hard, challenging, primarily because as we the PD of AGN are kind of featureless, they lack the features that we see, or when it's a lower shift, we can see that uh, the light from the AGN is contaminated by galaxy contribution, or sources are indeed varying. We have like different uh, problems when we try to find the even select and estimate the photometric redshift just from the SED template. So here I can show you a typical SED of a quasar with just 5 Sloan points, and where I am using the templates of SF et al. 2010 templates. So hence we came up with a new proof of concept. So this is how it started, and we took the light curve, we modeled it into using structure function, and this code people are famous. It's are aware of this code called Javelin. So we feed the Javelin with the light curve that we have, and it constrains the total variability into these two parameters: the total amplitude of the variability plus the characteristic time scale of the damped random walk. And this is our model. So this is such a famous model from McLeod et al. The whole formula, there are like additional two parameters. One is the redshift of course, and the other is the black hole mass. But then there is a particular set of constants or parameters that we can use such that it nullifies the black holes. And the whole dependency is on the rest frame wavelength and also on the dieback magnitude. So for the absolute dieback magnitude, to obtain that, that correction is being done using the galaxy templates by actually fitting kind of stuff from the templates of Asaf et al. 2010. And why particularly because we have these two parameters we get from the javelin or any the amplitude and the time scale. So these are indeed functions of redshift. So the time scale is a monotonic function, but the other one is a bit of increasing like a power law. So this is a very this is the work is still under progress. So this is how we came up with the idea that this really works. So what we did is that we took the real data of SDSS from for three bands G, R, and I. So we took the data from the data challenge of the HSN collaboration, if I got them, Richard, and also the CGF R band force photometry data, and we fed it into Javelin, and we did this test to prove that this works by doing it for 50 quasars from the Type 82, and this is an example of how Javelin models a light curve, and this is what we get from the um, combined PDF of G, R, and I band. So this is just the redshift prior. the photometric redshift prior and the dust lines are the spectroscopic redshift of that particular object. Well, it's pretty decent, yeah. But when we combine this with the SED priors that we obtain from different base, so here the SED prior comes from my SED fitting of using acid blade. It's not very well constrained, but when we combine these two, we get a really good posterior on the um, problem distribution function on the redshift that is pretty much very aligned and very well narrow with the spectroscopic redshift. And we came up with this idea that okay, the whole scenario works. But then, how fast are we? The Javelin, it's like 4 to 5 minutes per source, and we will be having millions of agents with LSST and stuff like that. I used to do that, and I run a few sources in the computer, and have nothing to do. So we came up with other algorithms to make it work in a much faster way. So that's when I started working with machine process. Particularly, I used this code of Collinberg, and it's pretty much like a question using the code algorithm called Synergies, and it could fit in light curve in about 19 to 20 seconds. So it's still a big difference between from 5 minutes to 20 seconds. Yeah. So then I was facing technical problems with comparing the results of Win uh, as well as Tau. So I started working with simulated light curve rather than going to the real light curve directly. So here I have a simulated light curve using damn random walk and the current result. And this is what we find. Uh, the dotted line are the two PDFs that are coming from the filter function and also from the time scale. And a combination of both is this solid line that gives the prior really good. So this is for a lower shift source and also for a higher shift. It works pretty decent, yeah, for this. And this is still a work in progress thing. And but we do have problems with a few sources like this. For example, here we have a really bad prior, but I'm trying to understand what exactly is failing there, or is there something that we are basically uh, fundamental mistakes that we are doing. I really want to show this to the community so that to the community that okay. So, for example, in this case, it's not really how do we say that? It's not really uh, giving us a bad redshift, but it's not very accurate. But we do have sources that has predicted in a very wrong way. But this will be fixed very soon. So the approach which I am planning to do is something like to draw redshift for MCMC. So when we give the light curve to a particular code called Topit or something, the how it models in such a way that the MCMC works and that has all the freedom, so that it goes all the way to the time scales and all the way through the acceptance and all. So that really gives us a it's something like it peaks at the correct tau, but the time is very long. So what I'm planning to do is to draw redshift. So for each redshift of McLeod tau infinity, so I'm going to give that as a prior. So that basically I constrain that I still say the MCMC, okay, you are not allowed to go to the other end. And immediately, if I could fix this thing with the simulated data, and I'll be going to test this for the real data from CT4 photometry and also with the Sloan Sloan light curves. And the future work is to create this tool, like a tool like Raphael or anything that could give you photometric redshift priors at once you feed in a light curve. And the second work is to produce the photography for all the voice agent catalog of Isabel 2018, which has variability information from any service like PDF or any others. And I leave the summary here, which is a variability-based tool to estimate the photometric redshift. Well, I should find a name, and ChatGPT gave me a few names. And thank you, and I had the privilege to visit last one with everything. See the mirrors, the commission camera, the secondary mirror, the primary, sorry, the main camera, and also a $1 million filter. Thank you.
Always the same people. I want to see new voice. I want to hear new voices. Katherine. Sorry.
How long? A really great talk, by the way. Super cool stuff. How long do you need? Like, do you need for your variability? Get these kind of measurements. Like,
Do you mean the baseline?
yeah.
Okay. So it totally depends on the number of data points. I totally believe with LSST, what we really need is something that could work with 1 year or 2 years data.
Thank you.
Yeah, but more accurate when we have more.
Yeah.
It always stings.
New faces, new voices.
It is.
Thanks for the talk. I'm just curious, what are the, if you go back when you're looking at your SDD and you're using, what information from here are you using in the variability, from the SDD fitting? You had some, are you just using like the flux normalization or?
Currently from the SDD fitting, I'm using not too many things, except I'm just using the Galaxy template to estimate the K.
Just the K
correction. Yeah, but this is just that the plot is just to show that it's pretty hard to get the redshift from the SED. And also with this is not the best SED fit, maybe. What I really want to show that when combining with a prior that comes from the SED, we are going to get a really good prior.
I was wondering, since if you use models like damp random walk or parameter from that, sometimes time scales are not really constrained if you take 1 or 2 years data. Did you test the performance with different masses to see if sometimes it works and maybe for stuff that varies on longer time scale, if it works, it's worse, your approach?
Well, when I was beginning, I tried to do something like I tried to put a cut here and try to see how it worked. Like just these 3 data points and these 3 data points. And I should say that it gave me a very broad prior. It's not very well constrained. So when we don't have a really good variability information, or if the sources are not really that much varying, it's like higher sources. So we'll get a really broad prior. It just can be used to say that, okay, this is not a low redshift.
Yes, thank you very much. It's really, really great idea, and I really encourage you to continue working. And I just want to follow up with basically what Mauricio said. To me, it seems that I mean, the question is whether this is sensitive to the data quality in terms of the cadence and the number of points, the length of the light curve, and maybe that it is.
It is. It is sensitive to the number of data points and the length and the cadence. That's why we think that a really good thing for doing this variability stuff.
Thank you. Really interesting. I'm trying to figure out what information from the variability used. Is it cosmological time dilation that essentially it's using?
Yeah.
It's so you're characterizing the variability, and you're saying it's at redshift of 2, so therefore the cosmological time dilation. If that's the case, how worried are you about changes in the variability with redshift? So the intrinsic variability of AGN, if that changes with redshift, does this still apply? Is that a concern?
well, the changes in the intrinsic variability of the AGN with Redshift.
Yeah. So yeah, so if a Redshift of 2 for some reason AGN variant on different timescales than at Redshift of 0, then your Redshift of 0 variability kind of knowledge can't give you time dilation or give you a different time. No, I appreciate sometimes it does. But if it's systematic, and I don't know, I don't know.
Sure. No, Paula can give a better.
So this is not going to solve that problem. Like you use proper spectroscopic surveys for that. This is just to have an idea of how accurate are the photosys, but nobody at the end will use photosys to answer that question. So for this, you will need to go to very detailed observations. So this is just to help with the photosys for large samples, but to answer your question, this is not the method. No, it's not obvious, but if we want to study this, it's not the method you will use.
We use as a prior. You can say for sure it cannot be in this range of redshift, or it cannot be there, and then you start to focus on what happens. Everything that can be taken as the amount of data that we have is something you cannot speak on.
Yeah, no, it wasn't necessarily criticism.
No, sure. It was a general question. Absolutely. Okay, so then we move on again on photosys. This time it's Katherine speaking about photosys for energy.
Gosh. Thank you. I don't know if I have this on right. Okay. Oh gosh, I understand now why everybody's standing up here. All right, I'm just going to start my. All right. Hi, everybody. My name is Katherine Kauma. I am a PhD student at the University of Cambridge Institute of Astronomy. And I'm here to talk to you guys today about photometric redshifts and selection for high Z quasars in the era of LSST, of course. So for me, high redshift is above redshift 4.5. We've got a lot of different definitions, but this is what I'm particularly interested in. And that's because these quasars are very good probes of the growth and formation of supermassive black holes. We find these really massive black holes and bright quasars at redshift 7, and that can help us learn about, and constrain the models for growth. Additionally, this is right around the end of the epoch of ionization at like redshift 6. And we can use quasars and quasar spectra to probe the changing ionization state of the universe. That also, I just think is really cool. But the thing about high redshift quasars is that there aren't a lot of them. They are faint, or at least fainter than our more local quasars, just because they're so far away. And they are rare. There just aren't as many of them as there are quasars in the local universe, because it takes time for a black hole to grow to the size needed to power a luminous quasar. So just to give you an idea of the current numbers, there are millions of quasars that we know over all redshifts, but above redshift 4, there's only about 4,500. Above redshift 5, we've got 1,000. At 6, it goes to 100, and above redshift 7, there are only 9. So LSST will be a game changer for the high redshift quasar field, as it will be for many others. So just in the first 6 months, it will go twice as deep as what I think is the most comparable all-sky optical survey, which is the ECAM. And in the first year, we expect
a tenfold increase in the number of quasars above Redshift 6. We're going from 300 to about 3,000. And above Redshift 7, we're looking at an increase from 9 to maybe 55. And this is based off of the J2016 quasar luminosity function. So that's really great. More quasars means we can do better science. We'll have more statistical samples. But it also means that we'll have more candidate quasars, and most of those will be contaminant sources, things that aren't actually quasars and that we don't care about. And the spectroscopy needed to, follow up and figure out, what are the quasars and their properties is really time and resource extensive. So we won't be able to get spectra of everything, which is, a common theme among these talks. So my project is focusing on what we can do and what can we do with the photometry from the first and second data releases from LSST. So these are just some of the things, but things like photometric redshifts, quasar luminosity functions, and efficient selection for interesting objects for follow-up. So traditionally, if you want a high redshift quasar, what you should do is, look at the colors. So a really important feature in a high redshift quasar spectrum is the imprint of intergalactic medium neutral hydrogen absorption that comes from intervening clouds of neutral hydrogen gas and the Lyman alpha forest. So as redshift increases, you get more and more absorption blueward of Lyman alpha until about redshift 5.86, where the end of reionization and like almost complete opacity with the Lyman alpha photons. So this is an example of what this looks like as you increase in redshift. So we have a we have model spectrum going up at different redshifts through the LSST filters. So you can see at redshift 4, it passes, the Lyman alpha passes out of the G band and into the R band. At redshift 6, it passes from the I band to the V band. And so you can use this and the effective drop in the photometry to find quasars using color. So this is an example of a color diagram used to select redshift 6 quasars. And you can see that the quasars are very, like in this very red area, sort of separate from the rest of the galaxies and things otherwise. So traditional color selection, traditional color selection is really good at finding high redshift quasars, and most high redshift quasars have been found using this method. However, it's also really, really good at finding things that aren't high redshift quasars, like ML-Y dwarfs, so like red and brown dwarfs, and red galaxies. So in high redshift quasar switches, it is pretty normal to see contamination rates of 70% or more. Additionally, color selection requires spectroscopy. So you can't get a redshift just from the color selection. And again, with your 70% contamination rate, you need to make sure what objects are actually quasars. And then finally, when you're using colors, you're using magnitudes, so you lose out on the information from negative fluxes, which is really important in your dropout bands. And then additionally, using colors as opposed to the combination of all of the photometric fluxes or whatever actually removes information. So you go from 4 data points to 2 data points when you go and do color plot. So my proposal is using SED fitting as an alternative to color selection for both selection and photometric redshifts. So the goals of this and my project is to have reliable quasar selection and foreground contaminant removal, and to also measure accurate photometric redshifts, luminosities, and reddening for quasar candidates. So our approach is to fit photometric data with quasar and contaminant SED models and determine likely high-Z quasar candidates for model comparison. This is very similar. Like this is SED fitting. It's not a new technique. However, the codes that exist now are optimized to fit the most things correctly. And when high redshift quasars make up generally less than 1% of that sample, they are often not fit as well. So we are using this as a way to, like this is tailored specifically for high redshift quasars and should, in theory, work better. So this is the general idea. We have our rest frame quasar model and a redshift and intergalactic medium absorption model that get combined, and we get a observed frame full SED. We pass that through the filters to get our synthetic photometry, and then we basically just do a simple least squares or chi-square minimization between our synthetic photometry and our data in order to find the best fit parameters, which are our redshift, luminosity, reddening. And additionally, out of this, we get goodness of fit metrics. So this is the model that I'm using. This is Matthew's models, the Temple 2021 models that quite a few of you are also using. And I focus on 3 independent parameters, which are the redshift, the luminosity, and the intrinsic reddening. And I tie an additional parameter to the luminosity, which is this I band magnitude at redshift 2, which basically under the hood controls the host galaxy contribution and the emission line strength. So by tying that to luminosity, we can create self-constrained Baldwin effect within the photometry. So yeah, this is just an example of how changing these parameters changes the spectrum. Yeah. So one thing that I did was one thing that I did was I realized when I was doing this fitting that the models, the quasar model SEDs weren't fitting well for higher redshifts. And basically, I realized that the IGM absorption models weren't calibrated for that high redshift and needed to be updated. So our general absorption model, we have a Lyman limit system, 912 angstroms, and the flux goes straight to 0 there. And then we have the Lyman alpha forest, and the rest of the Lyman series as well. And that is largely based off of the optical depth of Lyman alpha as a function of redshift. So in the blue, the original model that is used in the Temple quasar models, and that is only calibrated for below redshift 5. I found another model that is calibrated for above redshift 5, but they don't connect. So I thought the most thing to do was to just combine them, and this was relatively straightforward with a smoothly broken power law. Additionally, this is an improvement on both the commonly used around 1995 model and a more recent model by an et al., which you can see here. This is the Maddow model. So this has a pretty significant effect on the flux. So here, this is no absorption. This dashed line is the model, and then you go down to the Maddow model, which has not enough absorption here, but too much down further in the forest. And then my model in black and the Enjoy model, which are very similar. So now we get to the fitting. This is a simple least squares minimization. I want to make a point that this is not on a grid. I call a new function for every new parameter. It would be like if you're fitting a parabola. It's the same kind of idea. And then it's quick to me. I think objects fit in about a second. And I'm not looking at that many objects. Usually I put some preliminary code. So I can run through 15,000 objects. And what we get from this are our best fit parameters, parameter uncertainties, and goodness of fit metrics like chi-square and the BIC. Additionally, we can use MCMC to sample posterior distributions for these if we want to, say, look at an interesting object in more detail. So this is an example, spectroscopically, redshift 5.04. My photo Z gives us a redshift of 5.01. So these are my photometric redshifts for a testing sample of quasars. And so I looked at only the southern hemisphere, and I looked at, used the legacy survey DECAM GRIZ, the Vista near infrared with YJHK, and Y1 and Y2. We have about 12,000 objects above redshift 2.2, and my fits return 87% of the objects are within 5% of the redshift, which I'm very happy with. And you may notice there are these points where the spread gets really tight and where it's really wide. And these are a result of line alpha passing through the edges of filters. So that is when it's most constrained, and the least constrained is when it's sitting right in the middle of the filter. So I also wanted to look and see, like, if we're only using G, R, I, Z, and Y, like with LSST, what we get, and we still are able to get good redshifts on these objects. So that's promising. So I'll go quickly through this. The second part of this is modeling the contaminant sources, like the galaxies and the stars. Use the Swire galaxy templates and some BT settle dwarf star models, and then it's just done the same way. The galaxy quasar separations seems to work all right. This is old though, and I need to redo these tests. I haven't gotten to test the quasar and dwarf separation yet because I can't find a good sample of dwarf stars. So if anybody knows one, please let me know. And then for the future, I want to test on the eROSITA all-sky survey. This is an example of one of my fits. Again, 4.9, one spectrum, and the spectroscopic is 4.95. So, do I have time for, no time, okay.
You eat on the questions.
Okay, got it. Yeah, so basically, we can get spectroscopic redshifts without the need for near infrared, but the separation between the stars and the quasars is, we do need near infrared. So the combination of LSST with other programs would be essential. So these are my takeaways. Thank you.
Thank you, Katherine. Question?
Yeah, thank you for the nice talk. It was really interesting. So I have a curiosity question. So can your method can be applied for redshift quasars as well?
I think so. I haven't tested it below redshift like free, just because I haven't been working with any data sets that have the U band in it. So below that point with just GR, I said Y, it is like really poor fits. But I could try it with other ones and it may work. I don't know. I haven't tested it yet.
Thanks for the talk. So something that I've worked on in the past that really, like how tight your correlations are really awesome. There's a really well-known degeneracy between extinction and redshift, and so I'm wondering how you account for that, or how you've seen how that degeneracy comes into play in modeling. Maybe you don't have high enough redshift or extinction that it matters, or
yeah. So the max extinction that I allow my models to go up to is 0.2, and we do see so you can see sort of the degeneracies a little bit between EBB and Z. It's but It is there, and it is hard to break degeneracy. I found that my models are pretty, like, even with confirmed very highly reddened quasars, it can get the redshift to be pretty accurate while also capturing the fact that it is a reddened quasar. And you have the additional information from the infrared bands that help, just break the degeneracy.
More questions? Sure.
It's related and it might not be possible, but are you able to track the evolution of dust, the buildup of dust over redshift?
So I think that would be something really interesting to look at. But like the previous question, there is this degeneracy, and I think I would need to investigate and understand what the issue is further. I've run some test simulations where, and I find that it can recover, the initial distribution that I give it, but there is a significant amount of spread. Yeah, it would be really interesting to do. I'm not entirely sure. I think maybe it could be done if you've got a spectroscopic, like, confidently. But yeah, it's
More questions? We are actually, sorry.
Thank you. It's really interesting. So my question is, so presumably when you are shortward of the brick, then in many cases it's effectively a non-detection. Is it working with upper limits, or what are you giving it for non-detections?
so I am working in flux space. So when I get a non-detection, I do get a flux for these objects, and that is generally some very, very small number, or here, let me go back here, or even a negative number. And in the model, shortward of the line and break, we have 0 flux. And so essentially I fit with that. I include some amount of model quote unquote uncertainty that helps it not try to fit too closely to the 0 or the non, but yeah. So it's just 0 flux in the model, and then whatever flux I get back from the.
Would it be more helpful to use upper limits, or would you not think it would make any difference?
Maybe it might be useful to use the upper limits to inform the uncertainty on the flux, but I don't know. I haven't worked with upper limits before. Yeah.
Unless you are referring to say the depth be greater than some value, and that is actually we are entering in the discussion part.
Yeah.
Yeah.
The point is that the units as you move, we are that is in images, and then they try to recover the depth, and these are PGNs, and they are not quasar, but they are galaxies. So upper limits are extremely better if you are working the way which you need them.
You don't
with the large errors are more reliable than.
You don't necessarily. You don't have to necessarily assume the template for an upper limit.
This is the way in which the surveys of the text. More flux with huge error is more reliable than more money to put more into.
Okay.
The negative fluxes, colors, and photometry. We don't use only. It's not that we are losing information because we use colors and fluxes. So we actually multiply the information.
Yeah. It's a sort of general question. I guess that the IGM the opacity models based on the samples of quasar at very high rate, right? Maybe depending on the line of sight. So far we have a limited, the sky area, but obviously LSST opens up the, the whole sky. Then do you feel that the model could be revised significantly if we are getting more and more the sample, which requires spectroscopic sample, but we should rely on the photo-Z? Or you already have some good idea, okay, if you look at the whole sky, then, okay, so the current knowledge based on the limited line of sight should be good enough.
Yeah, so the IGM model is like an average, but definitely once you can see the error bars at the last couple points are very, very large. So when we get, more quasars at those high redshifts with LSST, we can, tighten up that relationship and get a better average one. That is another use case for finding high redshift quasars is, just testing along those lines of sight. The ionization is a function of, position.
Yeah, and just to follow up on that, I mean, really stressing the fact that these models are average models, and when each quasar is unique. So like for the IGM, its ionization is patchy. You are looking through individual clouds, right? And so when you look at the spectra, you see all the forest, and it is a forest, and it is So this is the trying to encapsulate the average behavior photometry, but there's definitely scatter around this. As far as the error bars at Redshift 6, I actually disagree with Katherine. I don't think it really matters whether it's 5, 6, 7, because the point is that's an exponential. And so basically your flux is going to 0 anyway at those high redshifts. It doesn't really matter exactly what the optical depth is. You're not seeing any line photons go through.
More questions. We have plenty of minutes. You can everything you wanted to know about photosynthesis. Oh, please. Say it again. Sorry. Yes, I need a coffee probably. First, I would like to have a question from somebody younger. Questions that you really want to know. It's the right safe environment to ask. You have all the experts here. Yes.
I'm just curious because obscured AGN are the thing I care about the most, and trying to do photos use them is something that like me. So I'm triggered, and I want to know what parameter, what in these models, what in data is the thing that's allowing you to sort of break this dependency between redshift and extinction. Is it because I mean EB minus E of 0.2 is obscured, and so is it? You tell me, please, someone.
I really wish that I'd included. I've got like a really nice example. I don't know what it is. I think, yeah, I don't know what it is. I think there still is some degeneracy there, but like with the combination of the rest of the SCP and not just the break, it really like the only way for them to fit it is to like change the EBV parameter. But let me see. Go back to my. It shows it'll go to the EBV thing. So the redshift is changing, that thing. Additionally, the EBV and the luminosity, or the luminosity, are very much related because if you look at the y-axis, it changes a lot with the EBV, and so our luminosity, our redshift, our EBV are all tied in some way. So I think that helps constrain parts of it.
Can I just, which kind of extinction laws you are using? Because having a Prevot and Calcetti make a huge difference, for example.
I am using
Yeah, so the extinction law is a empirically generated, specifically for quasars. It's basically a double power law, 1 over lambda, which was the slopes of the power laws were constrained from SDSS spectra in bins of y minus h color. And it's empirical. It's empirical, specifically tuned for AGN, which might address one of the questions why it's different. I think, but more fundamentally, to go back to Chris's question, like the point is, Catherine's using 3 parameters to fit. She's got at least 6 data points, and so yes, there's degeneracies, but there's enough data points there to start to break those degeneracies. And if they work by models, let's say the fact that models are good enough to do that is reassuring.
This is just a proposal. I don't work on very high redshift objects, but in the deep drilling fields, we have the VISTA surveys, right? VISTA, and those have a very good baseline. Like to compare with LSST, like the surveys started in 2009, so we will have 20 years. So if you care about the variability, you can compare in the Y band what you had from the VISTA survey and then LSST at the end. And high redshift, then you expect to see some variability. I think that's a possible way to break this.
I think we can then move on. Thanks, Katherine, again. Thanks for the conversations we had. Just to assure you that we are using, for all this work, we are using emission lines, we are using extinction from different models of IGN. We are taking into account, we are using fluxes and not money, so we are all on the same page, just to make the dots on the I. Okay, now we are changing wavelengths and surveys, and we go into Gaia DR4 with Maribel giving us an update on what we can expect from there.
Okay, Maribel, no, sorry. Shall I help you? Maribel, I speak about the glimpse into the future Gaia DR4 and about GM research. The overview of Gaia. Gaia was launched in December of 2013. The objective of the mission was our stellar mapping, create the most detailed three-dimensional map of the Milky Way and Nebula galaxies, and start cataloging, identify and catalog approximately 1 billion stars with an unprecedented precision in position and movement. The Gaia have 2 telescopes with a common focal plane operating at an angle of 116.5 each telescope has a primary mirror with a 1.45 meter per 0.5 aperture. The focal plane of Gaia contains 106 focal plane. But have 62 GCD for the precise measuring of stellar position and movement. Here, after the blue and red photometer for the spectra, the low resolution spectral, and for the V12 for the radial velocities. The passband of Gaia we can see here is the versus plane. The band in green is the G band is the range of 330 and 1050 nanometers, and the B in blue is the BP band the range is the 330 and 680 nanometers, and RP band is 640 and 1050 nanometers. Here we can see how is the animation of the nominal scan law of Gaia in 5 years. In the first 5 years of mission, we have around in the light curve about 70 points in G, BP, and RP band, and 40 points in the variability. Okay. Okay. The Gaia Data Processing Analysis Consortium, the PAC, have around 400 persons, have different coordination units. For example, the CU5 is for the photometric, CU3 for astrometric, CU6 for spectroscopic. And Claudia and me, we are in the CU7 for the variability parameters. We create the working package of the agents. Gaia have public data release and one early release. The first release published around the 3,000 variable star, the for months. The year two, they publish about 500,000 variable star with 22 months. The year three in 2022, we publish the light curve and variable information for variable stars. The baby start for months. In the Q7, we have different variable source. Have a different type of the star, the asteroid. In particular, we concentrate the ADAGNs. The agent is, we publish 9.5 million variable source. The 10% are agents. And here there are rotation and modulation source, pulsation, increasing system, and other. The other, there are the micro-latency and stellar objects. We are for the goal was the creation of a algorithm whose selection was based in Gaia data only and as soon as possible. We define the metric values are listed in the Gaia DR3 variation table. The parameters we publish is the fractional variability, the global function, and the error. So, but this is the Bloom parameters and the variation membership. The chart of the package, we arrive more or less 100, more than 100 million sort of classification. We take the time series. We decide that the sort with more than 20 points is good, but no, it's discarded. We take this source and calculate the different parameters. If the membership score is none, the source is discarded. If not, we take the source. In this case, we finally of this we have 34 million of source. After this, we decide cutting the color diagram and the different parameters. Finally, we publish the first clean, this is the Gaia variable IGN with 875 22,000 sources. In this catalog, we have 21,000 that are new identifications. This is an example of the Gaia-like curve. In green, we have at the G-band, the band, in blue, the band. This is a flat spectral quasar. Some people ask me how to get the R3 like curves. For this, you need to go to the archive. You want information of a single source, you can go in here. In this case, you put the coordinates or the name of the source. Here you can see the astrometry, the photometry, astrophysical parameters. You can see the like curve of this source. And here you have all information where this source, all information of the all catalog where this source is observed. If you want the all source of one catalog, you need to go to the search and advanced. Here the query. For example, here we select also the variation in our table. Here you create the table. You can design the format of your download. After you click here, table, or if you want to place the top 2,000 result, here you can see the subsidy, the all parameter of this table. But if you want to get the like curve, you go here and search associate data link, data link. But we have a problem because we solve table. You can't download more than 5,000 sources. Okay, we create a table, or in this case, you can the effect of the source. When you download the table, you download a single file for the source. Here you have the society, the dancing, the band, the time, mark, flux error, flux error, and the photometry and the variability. This is for eliminate the outliers, the strong outliers. If you want 5,000 sources, you have you go to data link products. Here there are download all like curves. But Gaia have the mean spectral. You can obtain the DRC mean spectral, yes, in the other you have here, and you can download it, but not calibrate. The number of public mean spectra in DR3 is 21 million. For calibrate, you have Gaia 5, and after you have the tutorial, there are the notebook. Here there are the calibrator. It's very easy to use. This is two examples of Gaia spectra for H alpha, H beta line. We fit this example with the Python fit. For news for DR4, we publish additional 20 new parameters. We will publish 66 months of data, but not only photometric. We publish photometric time series, spectroscopic time series, and astrometric time series. Before we can do the reverberation mapping with this spectral, and with the astrometric time series, we investigate do scenarios. In the first case, the radiolive experience, we investigate the possibility to detect the motion of the limiting feature propagating in the galactic jets. For example, there are examples of et al. 2021. On the second scenario, the radio quiet aging study relative to aging indicate that large scale modification in the accretion disk and the dust storage surrounding the central black hole can cause shifts in the photocenter. This example is Suchet et al. 2022. They obtained 41 source with proper motion bigger than 10. But see also Katimode et al. 2022, they cross-match Gaia and eROSITA. They obtained more than 2,200 stores with high proper motion. Other thing we can do with Gaia data, this in the free, but the DR4 is better. We investigate in the possibility the lensed quasar. We investigate the possibility to derive robust measurement of the time lag between the observed flux variation corresponding to the various images of a lensed quasar. Here are the sample. This is the J0501. This is image of Pan stars. This is image 1, the light curve of the image 2. The discrete correlation function between the image 1 and image 2 light curves. We obtain the 120 time delay between the image respect the image 1. Thank you very much. Suggestion welcome.
Thank you, Maribel. Questions? First, usual voices and voices. And then, now it's hard. Dragana was first. Thank you very much, Maribel, for this okay, coffee.
Coffee time.
Gaia dataset is really a wonderful data set to play with, and especially because you have also the spectroscopy, and it's a poor resolution spectroscopy, but then better than LSST, which will give us very poor resolution spectroscopy, which is 6 points. So I was just wondering, have you been trying to attempt to do some sub-classification of variable quasars? Like, for example, you showed this light curve of blazar, obviously, because there was this peak, very high amplitude in variability. So did you maybe explore this to put the flag if it is a blazar or?
No, it's very complicated. Classify only in general.
I have 2 quick questions. The first one, can we now go to the database and retrieve Lakers for non-variable objects?
Non-variable objects?
For instance, if the source is not in the variable catalogs, can we get the...
No.
Okay. No. And then for the variability selection, which features are you using?
For the DR3, the function, the quasovar, non-quasovar of the Battle and Bloom, and the slope extraction function. But in the DR4, we take the different papers, for example, your paper, and the Richard 2011, and I take the different features in the package of the Gaia. The idea is give this the IGN community for the machine learning. You have the table with all information for playing of the machine learning.
Thank you for a nice talk. I mean, DR3 is already great, and I'm really looking forward to DR4. I'm sure it's going to be amazing. My question is about the quasar candidate. 1 million candidates, whatever. Most of them have got redshifts published in DR3 from the BPRP spectrum, and I think it's fair to say it's a known problem where sometimes it misidentifies a line, and you end up aliasing with lots of spectral redshift from slow, spectral redshift from Gaia. You sort of have these diagonal lines, right? And so the question is inspired by Sarath's talk, right? You considered using the variability parameters from Gaia to aid in your spectroscopic measurement in the XP.
In the parameter with the XP spectral.
So in DR3, you published spectra for. Sorry, not you published.
But
you published
not
redshifts
for sun AGM, but the published spectra in general, not
Okay.
the GU7.
Maybe we can talk. Okay. Yeah.
More questions? When is the DR4 coming?
Presently 2026.
It's end middle because Sloan 5 is planning for the data release of the first data release of the South Hemisphere in the summer 2026. So are we going to
I don't know if that will play.
2026 is going to be great. Okay. And another questions, short, then we can break for a break. What does it mean having hyperpromotion for AGN? For me, that you really trust these 200 objects with a hyperpromotion for AGN. For me, it's a miscentering of the coordinates of the object. I can't believe that these are
yeah. This one. Because it's different.
We don't know what we are going to find. I mean, there are such claims of proportion. Some of this work sound reasonable. I mean, they investigate the objects which show hyperpromotion quite deeply. So this is why we asked to have astrometric time series. It's going to be a very difficult job, but we would like to see whether we can recognize some, ordered motion that can be connected to something happening inside the source. But I don't know. I cannot tell you if I believe that something is really happening.
Good. We are perfectly in time. We have half an hour sharp. So first of all, thanks to all the speakers and the people that were awake after a heavy lunch, heavy dinner yesterday. You have now half an hour to reset and hope to see you for my talk at 11:35. Thank you.
You're representing Neil?
Do you hear me? Oh, yeah. Okay.
So if you look at your programs, you'll see that I'm called Neil Brandt. I'm very happy to be here.
Just that I was me, right?
Yes, for one session only. We come in or yes. Okay, so final session, we're almost there. But by no means least, we have Mara Salvato talking to us about eROSITA.
Yes, thanks a lot. I think you can increase the volume because I tend to shout when I get excited. And for the health of your ears, it's better if I have less volume. So I'm going to give you an update on eROS1, so the first 6 months of eROSITA. And of course, the goal is to put everything in context with LSST. So I'm not giving really a scientific talk, but what is needed to be done in order to find and work on the AGNs, on the LSST. Before starting, of course, my work is in the name of the entire collaboration. I'm a spokesperson for eROSITA. There's a lot of people behind me, and I wanted that is clear. So let's enjoy. We have doesn't work. It is the middle, right? Is also off, probably. Not your fault. So let's enjoy 1 second in looking the Alp sky that we are allowed to share with you. As you know, eROSITA is split in two, German and Russia sky, and the Germans have released already the first 6 months. And I just wanted that you spend 1 minute, literally 1 minute, just to enjoy the view. Red is soft, blue is hard. Stop. So I'm going to speak about the about 800,000 actually point sources that are in eROSITA after removing all the extended sources from clusters or diffusion emission from outboard gas. Just put the eROSITA AGN in context, the usual plot show area and X-ray flux. Colored are for the pencil samples essentially. Usually you have very small area, very deep data, large area with very shallow, large area with very shallow data, and then you have eROSITA that is the entire gap here. This is the first 6 months, the South Ecliptic pole and the old sky depth. You can find here the values for the eROS 8. At the moment, we are at eROS 4.4 because then Ukraine and Russia war came in and we had observation, and I am probably one of the few that need the restart eventually and get all the eROS 8. This is the depth we are expecting at the end of the mission, and we are also expecting to provide the first hard sample of AGN. And the old figure that we put in the white paper in 2012 was showing the point sources from the pencil beam and all the area in Redshifts that will cover. There will be the quasar mode AGN, and they are here represented here. So this is the effect area, 140 square degrees, that we have released to the community already in 2022, and our observation were done at the depth of final eROS 8. So you can have from this picture an expectation of what is going to happen. For these bright objects, quasars, the spectra in X-ray bright can actually be used for doing science there. For the many more thousand objects at low luminosity, we are going to work with the stacking. And one point that we wanted to make is that the X-ray, although eROSITA is mostly strong in soft, it still allows you to get the data on AGN any other star would miss, because in all this figure is coded in Redshift, and all these low luminosity, low redshift images are dominated by the host, and you will not be able to distinguish the colors of AGN. So this population is completely missed by normal surveys. And because these are also nearby objects, in order to have them, extensively surveys that will not be present, because for these objects we need the area. So that's why eROSITA is going to be so cool. This is just something last say. eROSITA is going to be like Sloan for galaxy evolution, but this time is going to be for AGN evolution, the stacking and the grouping of all the sources under many features that you wanted to use. The ERAS-1 catalog was released in January, and the question that I heard most, more and more takes so long to get the counterpart catalog, and I wanted to make you remind that it is all sky, not points, so not pencil beam. So you need to have a control on main features first. Second, there are two users for our work. There are those that have already their own sample of object that they simply want to know whether or not the object is X-ray detected. And for them, we can provide the Rhinebeck of the counterparts and all the properties. But there are also those that wanted to do AGN evolution, luminosity function. And for those, you need to have a perfect control of the selection function and purity and completeness. And we're also preparing that in the catalog that is going to be released probably in September, when we have the eROSITA first international conference, and we are going to release this catalog. So I just want to give you an idea of how the work is done. First of all, for those that among us still do Rhinebeck match between any catalog and eROSITA X-ray survey, please don't do that unless you are working with the Chandra data. This is an example, a real one from XMM Cosmos. The red circles tells that within that area there is an X-ray emitter, and depending on the catalog that you use for making your association, either in E band, zeta band, or K band, you have a completely different source that is going to be your best counterpart. And this is going to screw your science. And you are going to make wild claims and then speculating hours and hours and trying to understand the meaning of this object, which actually was the wrong one. Because if I ask you which is the right counterpart here, who can tell me? Number one. You have to tell me number and letter. 1B, yeah, right, Rhinebeck check. No, it is not. The right counterpart is that one. And we know it because that was the right counterpart. But this is really telling you how dangerous is to have a Rhinebeck. So if you're making a check with Rhinebeck, eROSITA, ERAS-1 with your sources, at least 20-25% of your association are going to be wrong. So be patient and wait for my catalog to come up. And what we have done here is separating the problem into two parts. It is the Bayesian. So there are two components of the probability of the right counterpart to our sources. First of all, there is the astrometry part, where we take we keep in mind the separation between the sources in the primary catalog, which is eROSITA, and the secondary catalog, which is legacy survey 10, when we can, because these are the best data, the best that we can have, and unfortunately the galactic plane is not covered. Gaia, when we do not have legacy survey, and twice 2020. We take into account the separation between the objects, the positional error between for each of the sources, and the number density, because denser is the area, like in Gaia, you have beams of 3 million sources, denser is the catalog, higher is the probability that you have this association in your catalog. Then, after we have this part, there is the second part, which is the cool part, and we are going to use also for LSST, depending on me. What we have done is taking 14,000 X-ray sources from XMM and Chandra with secure counterpart. We took all the features from legacy survey for Gaia and analyzed independently and run independently around the forest and ask the question, what is our ability predict that an object is an X-ray emitter. As you can see, don't look at the diffusion matrix because just as a filler, just look at the numbers below. We have just using the SCD essentially of the legacy survey DRM. We are able having a record fraction of 87.4% with a leakage that is very small. The quality of the recall gets lower and lower because these surveys have very little features. Here you have few photometry and proper motion. Here you have 2 photometric bands, and even if you have 2 bands and a color is still not enough to get reliable things. But in this area, you can have a lot without having any need of using X-ray properties or separation from an X-ray source. So when Bozena at the beginning of the meeting on Monday was saying, is it still worth to try to identify AGN using optical and mid-infrared information? And the answer is yes. If you have a good training sample, this is the kind of accuracy that we can have in this area. Remember, legacy subject 10 has GR, Gaia properties when available, and W144 with the PSF homogenized photometry at the location of the optical meter. And these are fluxes, not mine. So there is a lot of features you can create in that way. So the first message that I wanted, at the end we have this catalog that provide for each source associated to eROSITA the probability is called PN in the N-way code that we have developed exactly for that in 2018, where we combine, as I said, probability from astrometry and probability by the prior. We provide the PN, but also we provide the purity and completeness value at different detection likelihood of the X-ray sources, because fainter is the X-ray source, higher is the probability that this is a false detection in X-ray, and the association then is, of course, also wrong. So all is already in the catalog, ready for you. So first message from between the connection LSST and eROSITA. The depth homogeneity and the fact that you're going to have a U and Y band from LSST is going to strengthen some of the counterparts and will change the weakest one that we have. We can already, as soon as we have the first LSST data, we will be able to create new samples of AGN. Just looking at how they are appearing, those that we already know how they appear in LSST features, and assign to every source in LSST what is the probability of being an X-ray emitter, what is the probability to be a blazer, what is the probability of being obscured AGN. So this is all machinery that can easily be used for this kind of purposes. And then the fact that if you take the first 6 months, for example, you're not going to be as deep as in 10 years, but the 6 months data are going to be great because they're going to be the least affected by variability, because all the SCD is going to be as close as possible to the real SCD and not affected by variability in some of the bands. So I'm really expecting ratings for making LSD and eROSITA together. One point that I want to bring up, and I was already bringing up on Monday, is the fact that we will not have WISE data for LSST, and I hope that during the discussion later we can bring it up again. Americans collaborators should really make an effort to get funding via NASA, ROSE, ADP, to get funding for making force photometry in WISE at the position of LSST, will make at least for the first 6 months of the summer. We have done work science with these catalogs already. We have released already the catalog of the hard selected samples. You see here the black one, the obscured AGN. You can see we are not as obscured of them. When we do the match with the BAT catalog, we managed indeed to get those that are unobscured, and only few of the obscured are detected. But this we know because of the soft focus of eROSITA 1. It's also true that this is just the first 6 months, and we can see more with the 4 passes. This is how the color curve appear for the distribution of the object. You can see already here the typical stars. This picture is very interesting. These are actually not AGN, or they can be AGN, but these are AGN in clusters, and this is what is telling that some of our X-ray point sources are actually unresolved clusters, and we have about 16,000 of them that are going to be released. All the rest are AGN. You can make a cut in photometry in order to have signal higher than 3 in all the bands, and this is the location. And then if you just look at the extended, quasars, AGN, extragalactic sources, this is the distribution. And it's really interesting to see the strange feature structure that are coming out here, and they are under study now. We have, of course, we have used this cattle also for identifying the blazars. In this work, Stephen Hammerich, all the catalogs that are known of confirmed or candidate blazer matched to eROSITA and extracted the properties from the catalog of counterparts. And I just wanted to bring up these numbers. So these were the numbers in total that we had. These are the Alp German sky. And just see here, so these are new association with ERAS1, and some are more than half are actually new association to X-ray flux. And if you look at the color plotting wise, you see that indeed the sources are exactly where they are supposed to be. So again, this is not done taking the object here and try to match them. These are blind association using properties and confirming posteriorly that they are of course, we are going to be at Redshift and combining methods that were presented in this week. We have already 5 on our site that are spectroscopic. There are other 3 that were appeared already by the same author, Julian Wolf. It was my PhD student and here a year ago. And we had more X-shooter time coming for confirming other objects that we have. I just want to bring up that before eROSITA, there were maybe 1 X-ray selected AGN Redshift 5, other were X-ray detections, follow-up of objects known to be at Redshift from optical surveys. These are blind search starting from the X-ray point of view, and with this you can make luminosity function, with the other you can't. So we are really populating the Redshift universe with eROSITA. People who need to have photosys, as we already mentioned, we discussed it this morning. And in my paper from IFEDS, I was showing how the quality degrade going from the area where we had HST photometry, kids deep photometry width-wise, and then on the rest of the sky where the data were shallow and we didn't have VHX, so this is very shallow compared to light. And we said we are never going to be better than that in the rest of the sky. And I actually proved wrong because in the paper that we are releasing, we also provide photosys, and you see that the multiplier is actually better than what I had in IFEDS, and the accuracy is the same here was 0.49. And how we did that, we moved from SED fitting using fluxes and colors. We went on machine learning and realized one fact. First of all, if you take a galaxy, an AGN, and a quasar, I want you to realize that many of the surveys provide you flux coming from a model, which is normally searched exponential or PSF. They are never together. And this is the azimuth profile of the object in black. And these are all the models that people are normally using. For a normal galaxy, you have at least 2 fits that can be more or less okay. For an AGN, there is none that work. Either you underestimate or overestimate the end of the galaxy, it's definitely the center, and only on the quasar you are going by. So this is a problem when people run photos using flux coming from total flux, model flux, unless you are working on quasars. And what is interesting instead is that for the legacy survey, one product that is available for everyone is the flux within aperture. And if you combine in each aperture the difference in colors for all the photometry that you have, you actually realize that there are trends that are different for the type of the galaxy. And they change with the distance or the size of the object, and this can be correlated directly with the redshift. And that is the reason why we managed to get those redshift. So bear in mind, instead of using 10 photometric points and relative colors, here we are using 285 features. They are all available by standard from the legacy survey. You can use the same for your work. And then, of course, as I was showing this morning, Raphael, it is a jump, a very easy jump, going from catalog photometry using colors in annulus, going directly on the image and get photos using the pixels of the residual of the galaxy around. And essentially, I am done. So I hope that should survive, Matthew, 1 minute. This is my summary consideration on the LSST and PhotoZ for AGN. We are going to be great because of the depth of the LSST data. We are going, at the moment, I didn't show the plot, but for legacy survey, it is true that I have great results, but as soon as I go on the faint end, my fraction of outliers increase because the data are not really homogeneous, and in certain bands I don't go beyond 23 magnitude, so LSST is going to be great also for that. We, however, need to have more information. So LSST is already providing aperture photometry, and sure that this is bottom flux not coming from models, unless it is a C model. So this is what Angela was showing the first day, and I was really surprised to see how the photometry was perfectly captured for star galaxy and AGN with the C model. But as far as we know, the C model is not among the outputs in the final catalog. And I know that the Italian colleagues are going to have a meeting probably tonight, if I understood correctly, where they're going to decide which requirement the output catalog should have. Please beg for us to have the C model as one of the outputs, because if they are going to provide exponential, devicular, OPSF, we are not going to work for the photos are going to be wrong. So this is really a dramatic, important point. And again, WISE is fundamental. And I think I'm done here, but if you want, I can speak more. Thank you.
Thank you very much, Mara. I'll start at the back if you haven't said yet, and then move forward. So if we start with Shanley, and then Paulina, and then.
Thanks for very helpful. So I want to ask for those around 20% that you cannot predict as X-ray sources from the optical. Do they have any
you're speaking, let me understand. You are speaking at the beginning. What are you?
Yeah, in the beginning, you showed that using the legacy
data. Yes.
The X-ray. So for those that you
not able to predict, do you have any sorry, let me go back there. This one. The confusion. Sorry. I didn't hear confusion. This one.
Yeah. So they're roughly like 30.
Yeah. But don't forget that this is before knowing the information that this object is closer to an X-ray emission. So the rest of the 13% comes from adding the probability coming from the astrometry. This is purely using all the information from the AC.
I see. So do you have any features in the PD?
Yeah, of course. Otherwise, I will not get 87.4. Okay. If there were no common features, I will not. So because the bands and the features are so many, I can create an SED here where I have only 3 bands, G, R, and B. Even if I combine them or use proper motion, my ability of finding common features is really small, and only for bright object in blue. This is 19 magnitude, this is 24. Right? These are completely different populations, these are not the same object. These are not here because Gaia is too shallow. Right? And here you are limited by the fact you have W1, W2, the color, and you are confusion limited because the data are practically almost homogeneous.
So another question. So you mentioned that there are 16 sources for the X-ray catalog are actually unresolved clusters.
Yeah.
So they're kind of super compact, like clusters.
Yeah, so they can be many things. So they are either compact or they are broken because the sources you start to see single sources in the nearby clusters, and we believe that they are single sources, and you realize that actually these are multiple sources coming from the same cluster.
I see. So what could be the X-ray source? Like hot ionized what could be the X-ray sources of these unresolved things?
This is coming from the plasma or from the AGN in the cluster.
Right?
Yeah, both type. We have 4 classes in the paper of Weiss that we're preparing where we distinguish all the cases.
Thanks, Mara. Third time that I dropped my computer.
Okay.
What was the C model, if you can remind us?
Yes, so this is actually something that I learned. The C model, as it is known in the income, it was a combination of normal models. From my understanding of what Angela said, the C model here is the 2 sources. And what Angela does, so basically one search captures the and the other the galaxy. And what is interesting is that when you compare with the work of Angela, the C model is going to be the same, but the output can change because the combination of 2 searches can be slightly different. But the C model captures that, and it is an intermediate product of the pipeline, but is not saved currently in the final catalog, and we need that.
Yep. And my other question is, when are we going to get images?
They are in optical, in X-ray. They are already there. They are already there. We gave it. Okay, so
everybody told me that you released the catalog.
We have raw data, reduced data, machine for re-reducing your data, variability, light curve, acid fitting in X-ray. Everything we had in EROS-1, you only find catalog association for cluster, for stars, different type of stars.
People told me it was only catalog.
No. You had everything that including the machinery and the manual for processing the data by yourself. We also have an upper limit page where you put your coordinates in and you can get the upper limits of the X-ray flux at that position. Just go in our page, everything is explained there. Thanks for asking because then I could advertise what we gave away.
Can you go back to your confusion matrices?
Yeah.
Okay. So the first question is this is highly imbalanced data set.
Yeah,
right?
we take into account.
Okay, so you're using the imbalance from
Yes, absolutely.
Okay. Second question. The numbers that once you predict with this model in the whole data set, not just the tanda sample.
Yeah, so absolutely. So all the purity and completeness that we have, we take all the sources, we randomize the coordinates, we re-put them in and use exactly the same model, and we compute what is the probability of getting a source that is randomly associated with the entire recipe. And this is what you're asking.
I mean, for instance, you have here, these are 14K Chandra counterparts, right? For which you know exactly.
Yes.
Okay, but if you go now to the whole sky and
Yes.
apply this,
Yeah,
the
so
numbers.
this is the result on the blind test. This is not the 14.
Okay.
This is the validation.
And then, but if you go this for all the sources in the sky, all the legacy survey sky,
yeah,
did you still get reasonable results?
I
mean,
don't.
for instance, as an example, in Alerce, whenever we create a model, we have the training set. Of course, that's a very small representation of the sky. Then you go to production and you check your predictions. Those they make sense.
Yes. So this is actually what I was trying to tell you in this slide here. What we have now is for every source in the legacy side, the probability of being an X-ray emitter. It can be lower and higher. Then that is combined with the vicinity to the eROSITA. But for all the sources, what is cool is that we have samples of objects that should have been X-ray emitted, and they are not. But then you do the stacking, you find that they are just below the X-ray part.
Okay, let's thank Mara again. Is Antonio? Is he online? Okay. I was going to say, I can't see him in the room.
Hi, Antonio.
Hi, can you hear me?
Yeah.
Okay, so I should share this, right?
Yeah.
Okay. I will try, so you can tell me if it's not. Wait a second. So first of all, I'm sorry for not being there. This is very unfortunate. I'm get a bit sick. Now, can you see the slides? Hello?
No.
No. Wait a second. Now?
Yeah.
Okay. Wait. Okay. Sorry. Oh. Okay. Okay. Now you should see them properly. Okay. Then thanks. As I said, I'm sorry being there. I'm starting this presentation, which is also the last one of this of the meeting, I would say. So I will try to be light and fast. And this is mostly on the synergies between the post-Rubin survey and the very high energy facility, which are represented by Cherenkov telescope, as you see in the background. And I will also tell you some details on a income project by UNAF on the not on the AGN group, but on the transient and variable star group that is by these people here. So just to tell you what we are discussing about, this is a typical spectral energy distribution of a bladder, just to let you put in a context which energies are we talking about. And this is the usual, this is kind of one, this is the usual spectral energy distribution, and you can see here the gamma ray section with represented by that high energy, very high energy emission of these blazars specifically. So just to give you also a context on which kind of, I mean, with Rubin and optical telescope, we are very most acquainted to have billions of sources. For high energy, this is like that. For example, here you have the sky as seen by the Fermi telescope, and you see the point sources, the galactic center, and the other sources. Just to give you an idea, these single blue points are single gamma ray photons, and sources are just a collection or statistical collection of more photons. And again, to give you an idea of what we are discussing, the constant function, the uncertainty of a single photon is almost represented by an Hubble deep field image, just to give you this kind of thing. So if we go and we look at which sources are represented in this gamma ray sky, and again, I repeat, this is Fermi-Lat, and we are talking about 100 MeV up to something like 10 MeV energies. Here you see, for example, some AGN represented by this gamma ray emission, and the majority of the sources in high energy are represented by blazars. So were discussed also yesterday in the afternoon session. And this are the majority, something like a few thousands of sources. Now, if we go to the higher energies, so we are now going to energies of 20 GeV up to 100 GeV, this is the sky that we see. To have these sources, to detect these sources, we use Cherenkov telescopes, and I will describe you shortly. And you see the number of sources are quite limited. We have something like 100 sources, and they are, apart from excluding the galactic center, where we have the usually remnant of supernova and other kind of sources, the extragalactic sky is mostly represented by blazars in the different classes, like high peak blazar, intermediate, F1, less portfolio present, so on and so forth. So this is the situation in the sky for the high energy, very high energy. And now I just, the next two slides, I give you just an idea of what is the TV astronomy with Cherenkov telescope. So how we detect very high energy photons. The scheme is quite simple. We have the gamma ray impact in the atmosphere, and the particle shower, which is produces a dimmed light, Cherenkov light, that you can see also represented here. This is a video, but okay, this is just enough to understand how it works. This light is reflected by the telescopes and analyzed by the camera. Now, the interesting thing here to keep in mind is that the atmosphere is the detector. It's not a telescope. The atmosphere is the detector. For this reason, the effective area of this instrument is huge, something like 10 to the 5 square meters, to be compared to the 1 square meter by Fermi-Lab. And which is the consequence of this? The main consequence is, as you can see in this plot, where you have the integration time, you have the flux sensitivity limit as a function of the integration time for CTA and for, which is one of the telescopes that I will show you later. And the Fermi-Lab, you see that there is a huge improvement in the sensitivity. What does it mean? It means that the Cherenkov telescopes are ideal to detect sources, variable sources, or for which, you need high sensitivity in a short time. Now, just to finish this broad picture of very high energy astronomy, I mentioned what also Yannis yesterday mentioned, the ideal absorption. It's the only backdrop of gamma ray, very high energy astronomy, that gamma rays interact with the background light and infrared and optical background light, and they are scattered. So that at the end you get a limited amount of light. Here in this plot, for example, you see how for some GRBs, which are the newest class detected by Cherenkov telescope, you see how the spectrum, which is the intrinsic spectrum, is like this, how it is modified by the extragalactic light from a small distance up to the highest distance. You see there is a big absorption, which impacts, of course, the observations very much. Now, these are the TV instruments. I include not just the Cherenkov telescope, but also other instruments that are in operation, for example, LASO and OAK, and of course the historical or present generation of telescopes, Cherenkov telescopes, which are MAGIC, HESS, and Veritas. And in the future, what we is also in a good timeline with the Rubin telescope. In the future, we have the Cherenkov telescope observatory. This observatory will have two different sites, in the north in La Palma and the south in Paranal, and they will be composed by different telescopes, and they will improve the sensitivity up to a factor 10, and then also the angular resolution, which goes down up to 3 minutes, and also the possibility to have a good field of view. All these conditions makes CTO a good instrument also for AGN, to study AGN. And to have an idea of which is the emission of AGN in the gamma rays, I use this sketch, which is often used to make understand where the gamma rays are produced and which process usually within produce gamma rays. And of course, the Gamma rays are the tracer of a non-thermal emission. Non-thermal emission means particle acceleration, can be electronic or can be agonic. So electrons accelerated and protons accelerated in the shocks or in other different processes that interact with the medium and produce by cascade other particles and also gamma rays. Of course, this is the process, but we are interested as astrophysicists to understand better which is the mechanism that is going to produce the accelerated the particles, for example, but also the composition of where are the protons, where are the electrons, which is how the jet is formed, and of course, which are among all of these proton, or other processes, which are the ones that dominate in the age and the gases we will observe. And all this information are what we usually do. We make, let's say, we have different diagnostic tools and the different methodologies. One of the methodologies is, for example, to produce a multi-wavelength set, what I have already shown you at the very beginning, which gives us an idea of which are the processes here. And then there are also possibility and necessity to monitor these sources, to check their flaring state and so on and so forth, and surveyed by Rubin LSST, a key player in this. Okay, just to remark, this is the same spectral energy distribution that I've shown you before, and you see that this is usually described by two major components plus the component of the galaxies or the host galaxy. And this the description of this emission allows us to give physical information on the source. How we do that? Usually we use monitoring or multi-wave campaign. It's an example. For example, here on the right, you see the different light curves along the, let me check, along yes, sorry, along 3,000, something like 10 years of data, and you see here in the very high energy X-rays, UV, optical, EVA, polarization, and polarization angle, and infrared. So these are our instruments to understand how the source works, also in the very high energy. And what we do is usually we need to monitor the TV blazers, and this is done at different wavelengths. And also what we need is a flare hunting of flares. To do that, the current of telescope are pointed instrument with a field of small field of view of fewer degrees, square degrees, to detect individual flares. We need surveys, for example, X-ray or GD surveys, but also the monitoring program. And of course, LSST here will be a key instrument. And just to also give you an idea of what we can do and what kind of information we get from gamma ray observations. Here I show you some light curve with a very short time variability. Why variability is connected to the emission, the size of the emission region. So when we detect such small variability, it means that the emission region is small enough. And of course, the modeling must take this into account to properly understand the emission. But another interesting feature that we can do with gamma rays, very high energy gamma rays, is, for example, to understand where the emission comes from. And in this specific observation of this flash spectrum quasar, which is characterized by powerful disk and with the Bergman region detected, What we see in the gamma rays, and you see here in this spectral energy distribution that goes from 1 GeV up to 1 TeV here, what we see is that there is an intrinsic spectrum, you correct by the EDL, is apart from the cutoff, intrinsic cutoff, there is no, it doesn't show any cutoff at the energies higher than 10 GeV. This is an indication that there is not an absorption by the ultraviolet radiation of the broadline region. So the conclusion is that the emission must come outside of the broadline region. Okay, these are just some a couple of results that I wanted to show you, just to give you an idea of what can be done. I am now just going to almost the end, describing you first of all the fact that with the CTIO, so the Cherenkov telescope array observatory, we also plan an unbiased survey, extragalactic survey, on a part of the sky of 10,000 square degrees, with a coverage of 1,000 hours approximately, where we expect to detect new sources. And of course, it will be very, very interesting if we could merge the information of this extragalactic survey, considering also the variability of the sources, with the LSST survey. And this is something that I think we should work on, trying to match, if possible, the two surveys. It will be great. And the other, and just a few slides, the last few slides is to mention to you the in-kind project that was done in the TUS Transformable Star, which is brought by the PI Angelo Antonelli and Paltavilla at ENAF. The goal, I'm not very much involved, I'm there, but not so much involved, but anyhow, the idea is definitely interesting, because the idea is to put together a bridge, as a matter of fact, to put together the multi-frequency and multi-messenger context that I have shown you how important it is to exploit the information contained in the high energy, but let me say also the Rubin data, the LSST data. How it was done, there was a preliminary work where there were some analysis of raw DP0 data, producing some alerts, and the idea is to match these alerts with the catalogs available at the Space Science Data Center. The Space Science Data Center, which is a public facility, you can invest and go there and download data or other tools, and they have the possibility to match many data from different instruments, high energy instruments in days. And here there are some preliminary results that were presented by Francesco Ragosta already a bit less than 1 year ago. The name is SNIDL, for monitoring, inspecting, limiting, and extracting alerts. The idea is the following. There is an example. Ragosta simulated a QF photometry by Rubin with the decaying source here. And what he did was to match this photometry with the spectra by LST that you can see here, with the spectral energy information available in the SSDC. This is just a part, this is the radio and the optical, but of course, as I told you, in case of blazars, we have also the highest energy part at higher frequencies. So this is the status of the project until last September. The idea was also to remove proceed removing possible artifacts from this analysis of raw data, but unfortunately, Ragosta was hired by another university, so since a few months, there were no any updates. So in case you are interested, someone who is interested for a new post position in this kind of work, in September the call should be out. You can also contact Giuseppe Alcavilla for more information. And so I am at the end, and this is a summary. And the summary is, I hope that extragalactic and pulsar science with Cherenkov telescope can provide great information on the black hole activity in sources like blazars, jet physics. And to do that, we need specifically multi-wavelength spectral energy distribution information, but also monitoring, optical monitoring of these sources, variable sources. And okay, the other very important to mention is that the Cherenkov Telescope Array Observatory will also be will deliver in the same period when Vera Rubin Telescope with operation will deliver higher quality gamma ray spectra and also monitor array of because maybe I did not mention properly, but we can also work on the other way around. In case we have monitoring of AGN by telescopes, then we can check in LSST data if there is anything interesting there, which maybe is even simpler. And then I finished describing you this description of the project. And I think that's all from my side. I don't know if you, since I do not have any feedback, I don't know. Can you hear me?
Can you hear me?
Very, wait a second. Please, can you repeat?
Thank you very much, Antonio. We have.
Thank you very much, Antonio, and I hope you will recover soon. And I want to make a comment. You mentioned that you found very rapid variability at high energy, which imply that the emitting region size is smaller than usually assumed the size of a jet. And I just want to comment that in our filamentary model, the transverse size of the jet is much smaller. So better explain the fact that we see such fast variability.
Yes, of course, Claudia. Of course, this is a possibility. In literature, there are other possibilities. You know, there are, for example, mini jets, so small regions which have, like with reconnection, magnetic reconnection, have a emission towards us, so that is enhanced. But there is also the famous Marshall model. There is the Marshall model with the small blob switching on and off. And but yes, of course, also the planetary model there is a possibility, and we have to go further to understand that these processes, of course.
Okay, so unless anyone else has any last questions, let's thank Antonio again, and I hope you recover soon.
Thanks.
And we can move into the final discussion session. I don't know if it was online. Perfect. So we have about
25.
Ciao. So we have about 25 minutes left on the program. I do want to finish strictly on time because we have to catch planes and trains. Wrap up at 1 o'clock. So yes, we have about 25 minutes of discussion. I would propose that we take 5 or 10 minutes as a discussion session, the multi-wavelength talks we just heard, and then spend the last 50 minutes or so discussing collaboration policies and application policy. If anyone would like to make any counter proposals, or is there anything else you could desperately like to discuss before we finish, can you speak now? No? Okay. Ah, welcome, Neil. Can you hear me, Neil?
Thanks. Yes, yes, I can hear you all, and I've very much been enjoying all the talks over YouTube. I've seen everything.
No, it's fine. We'll do that in 5 minutes' time. Okay.
Hi.
Okay, so let's kick things off. We've got. Has anyone got any questions, comments, discussion on the multi-wavelength synergies? I want to talk about infrared. Do you say stop?
I'm worried about my opinion on why. So Niels may be the right person to bring it up again. Do you mind to submit another proposal asking for force photometry wise to the location of the LSST sources? As American, you will be the right person to lead this project.
Okay. Has anyone in the room got any follow-up to that? I know Chris is probably. Oh.
This was actually part of my research proposal for the Catalyst Fellowship, and in an early AGN science collaboration meeting, Neil asked me if I had really given thought to how much work went into this, and I said no, because I probably wouldn't have proposed to do it. But I do do it. It's something that's very interesting, and I'm really interested in the infrared. I care about AGN, so talk after I really. I'm not sure yet.
So in order to have the project approved, need to be discussed next July, right? July 26th, and then they assign the money. Or this is already funding that you have, and you have already a postdoc for that. You want to do the work. You are the postdoc of yourself, okay? So then I really think that the starting point will really be the GitHub repository of Legacy Survey DR10, where they have already developed all the work going from optical to WISE. And we could do it at least for the first 6 months survey, because that has a comparable depth of the legacy survey as it is now, about 23 and 24 magnitude. And I think it is a worth for the community, but in general, not only for LSST, having this data is going to be fantastic. I'm ready to help you as much as I can. And Dustin Lang, I'm sure they will be super happy to help out, because I don't think I've met somebody gentle with this kind toward others need. Yeah, so he will be everything is open source there, so I really think it's the right point for us to start. Thanks. And Oni, I know that the UK with Amanda, they were doing something similar on sources, on the LSST sources with VHS. What is the status of that project?
Okay, from memory, I believe that the work that Raphael was doing with the Vista joint processing, that is picking up what Raphael was doing. They also have some funding to start exploring Euclid joint derived processing. Yeah. Yes. No. So yes, part of the UK's in-kind contribution is to do the joint Vista level pixel processing.
Yeah, so for those who don't know, I developed the pipeline for joint processing of LSST with VHS, other Vista surveys. The pipeline who is taking over that work and is going to run that. So it's just a case of waiting for LSST data to arrive and to run it.
Yes. So So that is currently being run in the UK, and so those products are available in the UK data access. UK data access center it's not set up for large numbers of users. It's still in testing phase. It will be all of the same types of fluxes that is done processed by the LSST pipeline. So the LSST pipeline can do it. It does do it. Then it will also be taking place, unless Raphael, you've switched any off.
C model is expensive, and I switched it on, and it is in there by default. So that if there's a question over CPU time,
I have problem with the on-off.
Every separate measurement you can switch on and off. C model is in there, and it's due to be run on both LSST. But it is true that whatever decision is made for LSST in general will probably copy it. So whether we would switch on measurements that aren't in the general catalog is probably likely. It could be done, but
we need to write a petition.
Well, see, I was very confused by your comment on C model because, as far as I can tell, and there are within the object table at the very least, the COAD object table, C model is in there. Oh, so in the product that you will have access to in the Rubin Science platform, you can access C model.
I was just based on Angela was saying. Okay. Yes, on Tuesday she said that this is not in the list of the output parameters.
Raphael wants to comment.
The confusion there is over DP0. I think it may have been excluded from the DP0 measurement. It is by default in the pipeline, and I think that's the confusion.
Okay.
Yeah, if we might lose Neil, but I can. Earlier in the week, I was going to show the table indicates all the different going to use different stages, whether that's data previews or whether it's in data release. But if I did that, I could lose Neil now because it's not on my computer.
Just being a responsible chair, checking that there's no one else on the floor who would like to join this discussion. No? Anyone else want to raise any issues regarding multi-wavelength or the X-rays or the high energies?
I think Neil's raised his hand.
Neil, please, of course.
No, sorry. I had a few things to say about the cadence, but I'll wait till it's the natural time.
Okay. Give Chris a chance to go through the proposed publication policy draft. Do you want to do that?
Sounds good.
Okay. Should we do that now then, Chris? And then, so can we get that PDF on the screen? Thank you. And put the
headset feels like talk about your car's extended warranty instead. This is how it works. Good to go. I don't think I've ever asked anyone if they can hear me. I think I also talk loud when I get excited. I don't know if you need to turn me down. So let's see. Oh, I guess I can. Okay. So the publication panel has been working on an update draft for the science collaboration. And so this is what I wanted to have a few minutes to talk about now, because for first, this is, like I said, it's a draft, which this document is meant to serve you. And so your comments are really important, everyone, because this is a document for the collaboration of all members of the collaboration. So please, if you have not read it, please do read it sometime in the near future. And if you have any comments, we'll step through kind of the goals of the document. And so if you have any comments, please email us or Slack us. I think Matthew put in the email that's sent around that you can email the panel, myself, Ilsang, and Don Schmieder. So let's see. Yeah, okay, here's the, you can click and bring, okay. So there's 4 main goals that we have. Oh. Ooh, that, oh yeah, it does. Okay. Oh, it's like Star Wars. Uh-oh. 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 Can arrow? Aha, drag. Okay, there we go. Dun, dun, dun. Okay. So there's 4 main goals, okay? The first one is to maximize validity. Okay, maximize. All right. So there is this huge collaboration. There's a reason why we have advisors and why people work together, is because the more people, the more perspective, the more you get out of the science. Okay. And so the number one goal is to ensure that we are, like it says, leveraging all of the experience here, which goes from senior to junior. 2 and 3 work together, protecting and recognizing. So the idea that we want this to be, this is the AGN Science collaboration, right? So we want to be able to talk amongst ourselves in these meetings, in Zoom calls, over Slack, wherever. And you should feel free and open to be able to express your ideas and know that you're going to get credit for them. Your work is protected. Other people are not going to. And then number 4 is to reduce the time for publication acceptance, because if you have all of these, perspectives, what's the thing, you get a paper, oh, this is something that the referee might question. Like, we can do all that ahead of time so that when it gets to submission, hopefully the review process is a faster route. Any questions on the big 4 main goals?
Or even comments. I mean, any big omissions? Anyone disagree? Agree? Is this a good starting point for how to build a publication community?
I have a small thing about point 4, because if you kind of put everybody like to talk about this particular article, you're going to have the opinion of 20 people to deal with instead of the opinion of one referee. And normally the referee will look into something to say to you about your paper. So I'm not sure that having a very wide open discussion about an article before submission will streamline the process. Quite the opposite.
I think later in the document, if I'm remembering correctly, we talk about the scope of who should request comments from, and I think it changes depending on the type of publication, and it's something that we definitely should think about. Please also, this is recorded, right? Is this being recorded? Right, so we don't need notes, so I won't forget all these great things. Okay.
No, but we're saving. This what Paulina said, that's very important because it can last forever. But maybe we could mitigate this by putting strict deadlines, like up to what.
There are later in the document.
Okay.
Yes.
Yeah, I went through the document very quickly, so I don't no comment in detail.
The place is in the document, and I don't know. But regarding point 2, for me, it's hard to see how this will be implemented in real life. Are you planning to, like, how is this gonna work? Like, first, people who propose gonna take the project, or because if we have been doing several times the same thing. So I don't know how you are proposing to solve that.
So I think it's together with the archive that we're creating, I think is going to create a place where people can see more, more visibility, what is being worked on. which is one aspect for that. And the second is like to be able to then, you can maybe collaborate on projects together. Like the idea that, the last summer meeting, Gordon said, hey, we're a collaboration, not a competition, but yes, being able to work on the same thing, like that is kind of partially baked into, there are issues that arise because of these things. You can contact the publication panel to arbitrate. But one of the main things is like, okay, you should be following AAS, ethics guidelines. And these are kind of like additional things that are stated for the Agent Science collaboration to like specifically so that as a member, you can think about it in a little bit more detail before just like stepping on someone's toes or taking a project or something. Implementing it, what it's meant to do and implementing it will be separate. And we want to try to, do those things together. So would be really glad to hear them.
Yeah, just regarding point 4, the comment that was made about point 4 is it depends on how somebody feels about when they receive comments. So, for example, if I give comments to my PhD student, I sort of expect them kind of to do it. But when I give comments to somebody who's just sent me a paper and they've just like invited me on, I don't necessarily expect them to implement. I say these are my suggestions. You don't have to do them. And so I'd hope that that's how people would feel. So look, I sent them to the Agent Science collaboration. People are able to send me comments, and I can choose whether to implement those changes or not. But then that also raises the point, well, if you've made a comment and you feel very, very strongly about it, can you pull yourself out of as in, you don't have to be an author on that bit, right? You can say, look, I made some suggestions, you haven't implemented them, I strongly disagree, respectfully strongly disagree. Please, I don't want to be on that paper. But I don't know whose names are going to be, and we haven't discussed this yet, and I imagine it's going to be later, whose names appear, like almost automatically.
Right.
Yeah.
Yes, you can always pull yourself off the paper. This is not meant to hold you to tie you to something. It's meant to open up, to more perspective, right? I think an author should, a lead author should, of course, read the comments, not be silent, not ignore them, say, hey, James, thank you, but for these reasons, we choose not to. This is the whole point, right? We're trying to build a collaborative environment where communication is maybe we bring up the level of communication between people, which is why we're implementing this archive, this project system.
Because to me, that's the difference between a referee process and collaborative suggestions. A referee essentially says, if you don't do that, this, it's not getting published, sunshine.
Right.
Whereas a collaboration doesn't say that.
I wanted to clarify that we, as a publication committee, cannot enforce anyone to follow any rule here, right? So basically all these 4 goals is sort of our statement, right? Okay, this is what we want to have and see. But everything else in the detail, for example, who's going to take whose comments and who's going to implement it or not, I guess it's a primary author on the list of the paper will decide it. But hopefully, they will have some reasonable mind to having the kind comments from the people to implement it. Of course, if they don't really wanted to do it, if they're the decision, they hopefully I will expect that they can explain individual the reason. And again, regarding the point of protect the intellectual property and foster the supportive environment. Yeah, again, we don't have the machinery any kind of rule to to have that. But again, as Chris said, we have some ethical guidelines, right? As a, doing an individual scientist, we wanted to see, okay, who's doing the what. Then if I'm working on particular things, for some reason, I might not be able to realize that somebody else is doing the similar thing, right? But if you are, as a whole collaboration, let's say, posting the ideas, making more transparent, then people who working on a particular project will realize that, okay, there's someone else doing the similar thing. Then naturally, by just forming the collaboration again, if it's such a nice environment, this is what we are trying to create it by just knowing, especially for the people, junior people working on a particular thing, easily just dominated by the big group. Okay, they're already working on, often neglected, right? We want to avoid that situation by just expose, the making everything visible. Then everything else is a people's judgment. If I were the person, I know that someone else, in particular, junior people working the similar thing, I certainly would like to contact and try to set up some sort of a nice collaboration. This is ideal situation. This is what we want to have. Again, there is no like rules or thing we can really enforce it, but at least this is our statement. That's what we are hoping to see in this collaboration.
Yeah, so I just wanted to share a little bit of wisdom from the Fermi collaboration, because we've been doing this for like 15 years now, and basically for point 4 it doesn't work, but all the papers end up being much better. It's just hit or miss. Sometimes you're right, the referee doesn't comment. Sometimes you just get stuck. So it's not, but so if you're in a hurry, it might be a problem. If you're not in a hurry, the paper is definitely going to be way. The way we deal with the second point is basically we have the scheme where you, in the collaboration sort of 2 meetings, there are 10-minute presentations. So before you start any project, or you're thinking about analysis, you started looking at something, you go the coordinator, you give a 2-minute presentation saying this is what I'm thinking of doing, and then invite people from the collaboration which have some expertise, or if you need some expertise, you can ask it there, and then they just make some entry in conference or some other page where people can that missed the meeting can go and see what projects are being actively worked on, and then they can join in, or if they have a similar idea, they can talk how to merge and maybe a similar thing implemented for people to know what everybody's working on, and just like you said, avoid stepping on people's.
That's chapter, I don't know, 4 or 5 or something. We have a Confluence style archival system for projects. That was one of the other things to talk about, but I'm running out of time.
I like very much the idea of presenting what you want to do before to everybody. And I want to raise. So one is that although this is a collaboration, and so we cannot force anybody to do anything, and we're separated from the Rubin project formally, we have to do some moral suasion to convince everybody to obey to these rules. Everybody feels protected in the sense that you are recognized because you're willing to share these rules with others, with some flexibility, of course, but so that this will be especially important when we will be on the borderline of, for instance, doing things with ancillary data, which is not totally clear if they're completely within the collaboration or not. And so the more open we are, I think, and with the best it is. The other thing is, of course, then we need some sort of guidance. Maybe it's already there. I'm sorry, about how do you include authorship based on suggestion, because maybe you receive 50 replies, and then there should be a balance between requesting authorship. I don't think this is a big problem, because in many collaboration, other projects in Euclid, we do that all the time. We show our interest in a project, and then one decides what contribution is given. So that's fair, but and
just to that comment, there
yes.
is some things in the off section. So if you could read them later and send your comments, what you think about that.
Okay. And the last, I think we have also to think about what will be the effect, in particular, publication that may arise linked to in-kind contribution. I think those are sensitive because in-kind contribution are for the whole community, but many of those, of course, are directed to us, like Angela's simulation or EST data can be by other teams. And so for those, it's not entirely clear to me who has the right to publish on it. And I'm assuming that although whoever is working on them is making the product public for everybody to use, on the other hand, they have their own idea also to work on that. So that those will be even more sensitive, that we have to create a collaborative environment so that we don't jump. We saw with Angela, everybody was interested in getting Angela's simulation, and I'm sure many of us want to check similar things. So that's particularly important to think about if for the in-kind we can follow just the same rules, or we have to be a little bit more careful also regarding Rubin policies.
Yeah, good point.
Okay, we have maybe 1 or 2 minutes left. If anyone's not said anything yet, would like to speak. Otherwise, as Chris said, please feel free to email Chris and Don any further comments or ideas. Last for Angelica, and then we can wrap up with Claudia.
Thank you so much to the publication committee for this, and as kind team, because Maurizio rose a question. We have exercised, if not all, but most of these points through our activity on the cadence of the cadence evaluation, and which was published in the APJ as LSST focus issue. On the first level, we have been, as kind team, obliged to interact with the recipients group, which is actually the collaboration. We are members of the two collaborations, TVS and AGN, and we in preparation of the special issue of this article, we have been interacting with Lynn Jones, Bill Clarkson, Rachel Street, Federica Bianco, receiving the first level of the input of our methodology and validation. Then we have been interacting with the AGN collaboration, sending the first draft of the paper, receiving wonderful comments from the maybe dozens of the members of the collaboration and the co-authors, and it really helped us, to maximize quality, reduce time for the publication, and all of these comments were, from our perspective, very supportive. We didn't find anything that can be in collision, and from this first experience, we didn't experience any, say, glitch or whatever. But of course, during the operations, when it is everything in rush, that can be different. Thank you.
Okay, thank you. Well, thank you to everyone who's voiced an opinion. As I say, this is very much it's for us, it's for the collaboration, it's for everyone here and everyone who's not here on the voting list. So we'll definitely be taking time to iterate and get feedback at all stages as we develop the details of this. But I think we're running out of time, so I'm going to hand over to Claudia for the last word. I'm aware people have to leave at 1 o'clock for flights, so we can let Claudia wrap up, and if
Yes, I just want to say that it has been really a pleasure to have you all here, and I thank you very, very much for coming, and I hope you had a great time. And I want to just make some acknowledgements. In particular to the INAF, our institute, and University of Naples, Federico II, for financial support. And I have to thank the people from the planetarium for hosting us, to help us, in particular the people there who supported us, streaming and all that. Thank you very much. And thanks to all the speakers, the chair that made an excellent work. And I just want to thank in particular two people who made a really good job and gave a major contribution for the organization and management of the meeting. So I would like to thank Maribel here. Thank you very much, very much. And the other one is, of course, Max. Not flowers for you, but why? So thank you again. Now have enjoyed the lunch, and then the buses will take you back to the city, and have a safe trip back. And Maurizio, want to say the last?
But before we do that, we should thank Claudia again for organizing everything. And I'm sure you all agree it's been a wonderful meeting, and indebted to Claudia for bringing us through in. Yes, if anyone does need to leave for travel or flights, please feel free to run away now. And if not, Neil, did you want to say something about the cadence?
How about this? Just to save time, I'll type it into the Slack, and that way people can look at it at their convenience, because people have other things on their mind at the moment. I'll put it in the Slack, and then we can go from there. Take care, everybody.
Okay, thank you very much, Neil. Lunch.